All right. So first of all, welcome everybody to the final day. Congratulations on finding this venue. It seems like some of us did not find this venue, so when they slink in, make sure to stare at them. Um, so as Ken said, my name's Mike. I'm a QEC researcher over at Google. And today it's my pleasure to tell you a little bit about an experiment that was published in Nature this past year that we ran, titled Suppressing Quantum Errors by Scaling a Surface Code Logical Qubit. Now, before I really even get started, I want to say that I work with one of the best teams I could imagine, and this was really an entire team effort. So from the people who made the device to the calibration engineers that were turning the knobs to make everything work just right, all the way up to little QEC researchers like me who would say things like, you know, the 2-qubit gate was twice as good, this would be a lot easier. They didn't really like that, but it's true. So they can deal with it. Like I said, I love this QEC conference. This is probably my favorite conference, or it was, up until Craig decided to start this war. So this is indeed a war. As you will know from Craig's talk yesterday, I will be talking about the runner-up in internet points. And for those of you, I think there are a lot of people here who could really turn the tide in this. And to those of you who could, I would say there's no way I would publicly ask or barter for internet points. So that's all I'll say about that. So anyway, at Google, we are all in on quantum error correction. We think that a useful quantum computer is very likely to be a fault-tolerant quantum computer. And so, obligatory roadmap slide. We have a series of milestones that are aimed at basically showing larger and larger demonstrations of quantum error correction. Now, the particular experiment I'm talking about today, we like to call a logical qubit prototype. And what it is basically we want to see some signature of error correction that we think is important or valuable. Now, that signature or metric that we frequently focus on is something that we like to call lambda. I honestly don't know where the name came from. I think it might have just been from one of Austin's papers back in the day. But lambda is roughly the error suppression factor you get when you increase your code to correct one more error. So in particular, why do we care about this? Well, this is the type of metric that we can use to extrapolate what sort of qubit footprints we might expect if we have some device performance. Now, in this particular talk, we're going to be focused on seeing a lambda greater than 1. So what does that mean? We want to see an example of making a device better, not by traveling along one of these lines, which I think everyone here has seen at least once or maybe even made 100 of over the course of their career, but also just making the device better by actually just making it larger, right? We really want to realize that promise of quantum error correction, which is to trade quantity for quality, supposing that the quality of the qubits or the quality of the device is sufficiently good. Now, we've done this before. In 2021, we looked at the repetition code, and I personally love the repetition code. If you are in an experimental group, I would run a repetition code. They're super cool. And what we saw in 2021 was that as we went from a distance 3 code all the way to a distance 11 code, the error rate went down by roughly a factor of 3 every time we increased the code to correct one extra error. So for the repetition code, that's a lot easier because that's 4 extra qubits per 2 code distance per 1 extra error correction. And so what we saw is that every time we added 4 qubits to the system, the error rate would go down by a factor of 3. So we started out with a 1% error rate, and we went all the way down to roughly 5 times 10 to the minus 5. And I just think that is super, I love doing these types of things because they really demonstrate that error correction is working, not just in this really noisy regime, but also in this low error limit. Now, of course, the surface code is a lot harder than the repetition code, as we all know. And it's also a lot more expensive to implement in terms of the overall qubit footprint. So today we're going to be focusing on just comparing 2 of the smallest iterations of the surface code, the distance 3 surface code, which can correct any one error using 17 physical qubits, and the distance 5 surface code, which can correct any 2 errors using 49 physical qubits. So we're going to triple the number of qubits and hopefully see the error rate not go up, which is typically what happens when you make a noisier system larger, but we want to see the error rate go down. And I would be remiss not to mention all of the amazing work that we've seen in the past year or two on quantum error correction experiments from other groups. I think this is one of the most exciting times to be in the field because we are really at that point where the devices are just getting of sufficient quality and just large enough that we're starting to see really exciting demonstrations of quantum error correction. So yeah, I think it's very exciting. Okay, so disclaimer, I am a theorist. But in particular, I wanted to tell you a little bit about a bird's eye view, a theorist's point of view of how our qubits work at a high level, and some of the problems or some of the difficulties we have with controlling them. So to start off with, no surprises here. Our group works with superconducting transmon qubits. You can think of those transmons as basically harmonic oscillators with a little bit of nonlinearity. So these nonlinear superconducting oscillators, this nonlinearity is very small, but it allows us to use the bottom two energy states as our qubit. Leakage is something that we worry about all the time because it's really easy to accidentally drive into those higher energy states, but this is sufficient for building a qubit. Now on the right-hand side, we actually use tunable qubits. And that's actually really the name of the game for us. We really like to make everything as configurable as we can. So we use a lot of tunable components in our architecture, which will be very helpful. I mean, it actually is the basis for many of our gates, our readout, et cetera. And so it allows us to basically make the system as good as we can after it's constructed. Now, the first thing you should ask yourself when you have qubits is, how good are the coherence times? Because that's going to be a major limiting factor for what error rates you're going to see. So the reality is that our qubit coherence times are not that good. Compared to the rest of the field, we see regularly coherence times in excess of 100 microseconds. But in this device that we constructed a year ago, the average T1 was about 20 microseconds, and it ranged from about 13 microseconds to 27 microseconds. And the T2 times range from about 15 microseconds to 52 microseconds, with an average about 30 microseconds. Now, if you convert that to a Pauli error, that corresponds to, since this is a error correction theory folk, that corresponds to an error of about 3 times 10 to the minus 5 per nanosecond. Now, 3 times 10 to the minus 5 is a small number, but a nanosecond is a pretty short amount of time, even on the time scales of our devices, which are pretty fast. And so I was just talking to Matt literally before I came on stage, and he said, imagine if we knew what we were doing, what we would be able to achieve. So this is something that we absolutely have to fix as we move forward. Now, the way that we do our single qubit gates is we just drive some microwave frequency at the frequency of the qubit. And as our 2 qubit gates are done by basically allowing two transmons to swap photons. So that's not shown here, but we capacitively couple two transmons to a tunable coupling circuit, so another tunable transmon. And we bring this 1-1 state on resonance with a 0-2 state, and we allow these photons to swap. And as we process around back to the 1-1 state, we impart a -1 phase, and that gives us our CZ gate. Now, the first thing you should think about when you look at this circuit is, well, you're intentionally coupling to a leaked state to do your 2 qubit gate, and this is true. So we really do need to be very, very careful about leakage in our system. And as you heard from Matt on Wednesday, wouldn't it be nice if we had an error correction scheme that used gates that didn't couple to the leaked states? For example, an I-swap gate. And so I think this is a really exciting example of, even in the short term sort of theory work, being able to inform interesting design decisions at the hardware level and really being motivated by those decisions. So I think that's an exciting sort of route to explore. Okay, but of course, these CZ gates don't live in a vacuum, right? We have to execute many CZ gates in parallel to do error correction. And also, the qubits, depending on what frequency they're at, behave very differently. So the thing I want to impart with this slide, on the right-hand side, you see a plot of different qubits, where the T1 is on the y-axis and the qubit frequency is on the x-axis. And depending on where you park your qubits, they're going to get very different performance. And this is due to resonances with things like TLS defects. And so in particular, if you want to apply some circuit, as you can see on the left, our qubit frequencies basically carve out a pretty complicated dance, where they start out with some idle frequency where we apply single qubit gates, and then we move them around, trying to couple them to the things we want to couple them to, not couple them to the things that we don't, and avoid places in frequency space that are just bad to be. And so in particular, this really is quite a difficult optimization problem and something that we work on to try to get the best performance that we can. Now, measuring the qubit state is pretty simple. So we talked about single qubit gates, 2 qubit gates, the transmon coherence. For measuring, our qubits are coupled to a readout resonator, and the frequency of that resonator will depend on the qubit state. So we can send in some probe tone, and when we see the amplitude and phase shift that comes out, that gives us the information that we need to infer whether the qubit was in the 0 state or the 1 state. Now, I just want to pause here and say, for those error correction folks out there, This is the type of thing that is very, very helpful information, for example, for error correction. And there have been a ton of really nice works that I've listed on the bottom showing that this can be beneficial to use in, for example, decoding. Now, this plot, kind of a famous plot that you'll see pretty frequently from a superconducting qubit talk, is what we call an IQ plot. Here, we've plotted those phase and amplitudes for those complex signals for when we prepare the 0 state in blue, and when we prepare the 1 state in red. And you can see that it forms these two clouds that you can separate, and from those two clouds, you can draw some classifying line. Now, if the IQ point that you get is to the right of that line, you declare, well, probably my qubit was in the 1 state, and if it's to the left, I declare probably my qubit was in the 0 state. And again, if you have some point that's right on that classifying line, you should say, I don't really trust you. And that's extra information you can give to your error correction protocol. The other thing I'll mention, of course, is that you'll notice there are a lot of red dots in the blue cloud, and that's just, our qubits are losing energy, and so our 1 state readout is considerably has less fidelity than our 0 state readout. Okay, so those are kind of the components of our device. And so what does the error correction experiment actually looks like? How do we sandwich these components together to run a surface code? Well, our surface code consists of a pretty standard circuit of 4 CZ gates sandwiched between 4 layers of single qubit gates. There's actually more going on, but roughly this is what it is. One thing that I'll note straight away is you'll notice that there are kind of Hadamard gates missing on the data qubit towards the end of the cycle and the beginning of the cycle. That's because we want those Hadamard gates to cancel. We can cancel them out, and so actually the state that we occupy while we're measuring and resetting the qubit is the XZZX surface code, which is this nice surface code that was used for in the context of bias noise. It also has the nice property that the sort of idling bases look like alternating patterns of X and Z, so really the two bases aren't really distinguishable except for inhomogeneity in the device. So this is really not drawn to time scale. Our gates are significantly faster than our measure and reset moments, which are far and away the longest parts of our cycle. So in particular, if you look at our readout and reset time, that comprises 2/3 of the total cycle time of about 1,000 microseconds. These are rough numbers. I think the actual number is like 921 nanosecond cycle time. And then if you look at the errors that we see in our device using things like XEB benchmarking or randomized benchmarking, you see a Pauli error for the single qubit gates of about 10 to the -3. Our 2 qubit gate has an error rate of about 6 times 10 to the -3. Our measurements are significantly noisier. Measurements tend to be noisier in superconducting qubits. It's about 2 times 10 to the -2. And then, of course, this annoying line called dynamical decoupling, so DD in yellow. And what this corresponds to is the data qubits just hanging out, waiting for the measure qubits to be measured and reset. Right? And as they're hanging out over that long period of time, we apply some echo sequence to prevent decoherence as best we can, but they accumulate an error of about 2.5% over that period. And again, I want to come back to this. This is again that T1 time kind of rearing its ugly head, right? Because over 650 nanoseconds, if you remember that 3 times 10 to the -5 Pauli error, that's about a 2% error that we're incurring just from the qubits idling during this long period. So it's something that we really want to fix up moving forward. Okay, so I think those numbers are pretty interesting because if you ever wanted to run a Pauli simulation and say, how well our device is doing now, you could do it. Take those numbers, plug them into your favorite STIM circuit, you'll get an idea of how our devices are doing at the logical level. But of course, these individual component benchmarks aren't necessarily indicative of what happens when you run everything in context together. So a metric, or a first-order metric that we like to use to quantify how our device is doing is something that we call the detection event fraction. So you heard about detectors from like 7 different people now, but just to remind you, a detector is a comparison of measurements that in the absence of errors should be deterministic, and a detection event is when they don't. So a detection event happens when some error has occurred. So you can use that information to try to figure out which parts of your device are noisier than others. So if you resolve that information in space, as you can see in the middle here, you'll see that the brighter parts of the chip are the noisier ones. So indeed what we're seeing is that the left bottom side of the chip is quite a bit noisier than the right top side of the chip. Now, even more importantly, you can resolve that information in time. And you'll see that here the dark lines all correspond to, so the dark blue corresponds to different distance, weight force stabilizers. And the light cyan lines correspond to weight 2 stabilizers. They have less detection of infraction. They're checking half as many qubits. The dark lines are the averages of all of those numbers. And what you'll notice, kind of annoyingly, is that the detection of infraction is going up over the 25 cycles where we're running error correction. Now, what we think that is leakage happening in the system, depositing errors where it will, maybe causing other leakage. And this is something that we absolutely need to address in order to scale to much longer experiments, right? One of the hypotheses of error correction working is that, well, your device shouldn't get worse over time. So this is super important. We do see that it almost reaches some steady state population because we see a characteristic rise time of 5 cycles. But again, this is something that you really need to keep an eye on to make sure that your device isn't going to get worse as you run longer experiments. Now, the other thing that we really need to have happen is that, well, we're going to trade quantity for quality. So as we make the chip bigger, the error rate shouldn't go up, the effective physical error rate. So we compared the distance 3 codes to the distance 5 code to see if the effective detection of infraction we were seeing was in fact higher or lower than the distance 5 code itself. And what we saw is that, unsurprisingly, the distance 3 codes were slightly less noisy. It's pretty easy to see how that could happen. For example, there are unwanted crosstalk that's not present in the distance 3 codes, but present in the distance 5 code. But in general, the detection of infractions stayed pretty similar. And that's actually really promising, I think. It means that, well, we can actually scale up in space because as we make larger and larger chips, we expect the effective error rate to remain roughly the same, the effective physical error rate. Now, when we were actually running this experiment, ideally, what we would do is we would compare a distance 3 code that had exactly the same error model as a distance 5 code. But as we can see from these pictures, the distance 5 code kind of has this rather inhomogeneous error model. And so what we chose to do, which we think is reasonable, is we just chose 4 distance 3 codes on the 4 quadrants of the code to minimize their overlap, but represent kind of the performance of the entire device and compare it to their average. OK, so we've talked about component level benchmarks. We've talked about sort of a systematic benchmark or a benchmark that's in the context of running error correction. But what about that top line number that we care about, right? At the end of the day, we care about the logical error the marginal amount of logical error that is increased every time you do an extra round of error correction. So that logical error per round. And back when this experiment was kind of young, when we were first starting, and the device was performing worse, we performed a simulation, a pretty simple density matrix simulation of our distance 5 code. So 49 qubits, but you have to condense it down into 26 qubits using some tricks, or else you can't do it. And what we see is that if you use a really simple error model consisting of just T1 and T2, some crosstalk that we know is always there in our system, some leakage, we were predicting an error rate of around 2%. But when we were running the experiment, we were seeing the error rate on the order of 7.6%. So that's almost a factor of 4 higher. That's not so good. And so we need to start looking at our component level benchmarks to assess, what's going on? Why are we so far from what we would expect in this simple model? So for example, we could look at single qubit RB and see that, well, the error that we're seeing effectively in our single qubit gates is quite a bit higher than what we would have expected from the coherence limit. It's kind of a similar story for the 2 qubit gate. And so we would add some extra depolarizing error to account for this extra error. This is one of my favorite things that we do. So this is an experiment that we call leakage slicing. And what it is we basically run an error correction experiment. And at every point in the experiment, we measure all the qubits using measurements that can discriminate the 0 and 1 state from the 2 state and higher. And so we see how much leakage is accumulating in the device. And over these first 3 cycles, the data qubit is on the left-hand side here in the blue. We see that leakage is slowly accumulating in these data qubits, which we don't like. And then for the measure qubits, we have this step function that corresponds to the measure qubits kind of rising up, and then we have the end of the cycle where you have the dotted line, and they're being reset. So leakage is being extracted from the system. They rise up, they extract, and so on and so forth. And I'll come back to sort of the leakage in the data qubits later. And finally, we have, well, if we look at the extra idle error, the error of the data qubits as we are measuring and resetting the measure qubits, we see that it's quite a bit higher than what we would have predicted from T1 and T2. It's not terribly surprising. Something's happening. You're measuring a subset of qubits on the grid. Things like readout crosstalk can happen. But when you add all these errors back into the error model, you see that indeed our experiment is behaving, where these simulations can pretty well predict the logical error rate of the experiment. But at the same time, really what we're doing is we're looking at individual components and creating these fudge factors. And what we want to ultimately do is we want to get performance in the device that is reminiscent of what we think its sort of limit is, which is this 2% number. And so a lot of what the work on this project was trying to get that number back down to what we think is close to best case performance. Now, it bears repeating, but that 2% number, it's not as low as we'd like it. And so this is kind of setting what I would say is a low ceiling for this device. But with the configurability of the device, we are able to get close to that ceiling in order to see beneficial error correction. And I think I've run simulations before where I've looked at this number, and if we assume the device was performing just as well as it could, we would get like a lambda factor of roughly 2. And of course, you'll never get to that limit, but it kind of gives you an idea of how good we need to make this device in order to hit the sort of metric that we want, which is lambda greater than 1. Okay, so maybe it shouldn't be surprising to you because I'm up here, but the TLDR is that we succeeded in doing this. So we ran an experiment where the distance 5 code outperformed the average of the distance 3 codes over varying numbers of rounds. So in particular, looking at this plot, this is kind of the main plot from the paper. Every blue pentagon corresponds to a distance 5 code running from 1 to 25 rounds in steps of 2. And the red triangles correspond to the distance 3 code. So the dark red triangles are the average of the distance 3s. The light red triangles are all of the 4 different possible distance 3s in each quadrant. And so we see that not only is the error rate better, but also if we plot the error per round, so the extra error that we obtain in every step, the distance 5 code does about 5% better than the distance 3 code. Now, 5% better is not going to get you to 10 to the minus 12. But what it does mean is that we're at a point where we're just seeing devices that are sufficiently high fidelity so that the error rate and sufficiently large that you can actually run the experiment. I guess I should have mentioned this before, but this was all run on a 72-qubit Sycamore processor. But the fidelities are just good enough and the processors are just big enough where we can see the error rate go down, not because we're making the processor better, but because we're making the processor bigger. And I think that's a really important thing to drive home. Now, in particular, the logical error per cycle we end up seeing is about, well, when we first ran the experiment, it was 2.9%. I'll show slightly updated results in a bit. But in particular, one of the things that you really have to worry about when you're running an experiment like this and you're right on the line is all the ways that you can accidentally bias yourself in one direction. So one thing, for example, that I would like to emphasize is that you have to be careful with really, really short error correction experiments. If you looked at our first round of error correction, the distance 5 code performed twice as well as the distance 3 code. And so if you want to sort of extrapolate your device performance using this lambda figure, you should be extrapolating from a lambda figure you get by running many rounds of error correction, hopefully even more than 25, which is where we got up to. Okay, so this is an error correction conference, so here's a little bit of decoding jazz for you. So as many of you know, when we plot those points on those error curves, we are implicitly using some decoder. The decoder that we chose to use, because we were interested in the absolute best performance of the device, was a tensor network decoder. Right? These are rather famously get close to maximum likelihood inference. And the way that we created this tensor network decoder was we started with a Tanner graph of the circuit that we actually implement for this surface code. So on the left-hand side, we have error mechanisms in red. And on the right-hand side, we have detectors. And an error mechanism is connected to a detector if it sets that detector off or it activates it. Now, to actually get the errors that the error probabilities that we put into the error mechanisms, we used a method called PIJ, where we basically look at the device data and let the device tell us what sort of errors are happening. We found that that was a little bit better than trying to use, for example, RB benchmarks to set these numbers. Now, we can easily turn this circuit-level Tanner graph into a tensor network that contracts to the likelihood of some set of syndromes evaluating to something that has flipped the logical observable and also something that hasn't flipped the logical observable. And the way that we can do that is we basically replace every error mechanism with a delta tensor. So some tensor that's weighted by the probability that we use getting PIJ, and the detectors become parity tensors. They basically choose out the Feynman paths that are consistent with the syndrome that we see. Now, we need some kind of way of contracting this network. Contracting it exactly, this one you'd be fine. For much bigger ones, you'd be amazed at how quickly this becomes unwieldy. So what we do is we actually expand this network out as a series of matrix product states by taking every detector and expanding it as a bond dimension 2 matrix product state. This is super important for one of these detectors, which is secretly the logical observable, because it connects to many error mechanisms. So just the dimension of that tensor would be super high if you didn't have some sparse representation for it. And then we take these series of matrix product states and we contract them, sweeping along, keeping some fixed bond dimension using sort of a standard technique from DMRG. And then we evolve with some fixed bond dimension that's about 30, and we see that the tensor network converges on the largest system sizes that we look at. Now, one thing that I want to emphasize with this method is that this is extremely far from a real-time or fast decoder. I don't even want to tell you how long this took, but it took a while. And this picture might look on the left like it's not so bad, but this is the red and orange dots correspond to a distance 3 one-round experiment. This is a distance 3 10-round experiment. That central node is the logical observable. I couldn't even get a distance 5 25 round because in the 3D thing wouldn't render. So these are really annoying tensor networks to contract. And in the future, ultimately we want to be comparing our performance against decoders that run in real time because that's how we're actually going to execute non-Clifford gates or non-Clifford circuits. Oh, sorry, and I want to mention there was a really awesome poster I saw from work that was recently published that I just want to point out because I think it's really cool, and they, I think that they're really kind of pushing forward what's possible with these tensor network decoders. Okay, so of course, the tensor network is not the only decoder that we tried to implement. We used various flavors of minimally perfect matching. I've definitely run unifying on this data set before. And what we saw is pretty cool, is that as we increased the sophistication of the decoder, the error rate of the distance 5 code went down as the error rate of the distance 3 code, right? So they're both coming down, but the distance 5 code actually its performance got better faster than the distance 3 code, which is kind of what you'd expect, but it's really nice to see. And the other thing that I want to mention is that there's this other nice decoder that we took from the literature. There was these nice papers by Higgett et al. And Krieger et al. Called belief matching, which is basically you glue belief propagation, which is like one of the best ways of decoding classical LDPC codes. You take minimally perfect matching, which is one of the best ways of decoding the surface code. You literally just shove them together, kind of glossing over the details. And it performs really well. So that's something that in principle could be a lot faster. And even using that decoder, we saw the distance 5 code would outperform the distance 3. So that's pretty cool as well. Now, something that we've actually been looking at a little bit more recently is decoding with machine learning. So we talked to some of our friends over at Google DeepMind, told them about error correction, and they say, that error correction, that sounds an awful lot like a classification task. Maybe we can build a neural net to decode the surface code. And they're pretty clever, and so they came up with this pretty awesome sort of neural network architecture. It's a recurrent neural network with transformers under the hood that learns to decode the surface code. And what they saw was, which was pretty interesting, so the first thing they tried was, let's try to train on the device data. And that just did not work. There is not enough device data that we had in the experiment for their decoders to kind of figure out what to do. But then they had the pretty clever idea saying, well, you generate some prior for your decoders. Let's use that prior to generate synthetic data, train the decoder up to some point, and then use that precious but limited device level data to teach it a little bit extra. So on the right-hand side here, you see a list of different decoders. And one thing that I want to mention is that the axis is not starting at 0. So these differences are a little bit smaller than they might seem. But it does, in fact, end up being the best decoder that we have right now. As we start from the gray on the left, that's vanilla minimally perfect matching, going all the way to black in the tensor network. And on the left-hand side, we have the pink bar, which is that machine learning decoder trained just on synthetic data. So because the tensor network is a maximum likelihood inference engine, we would not expect that to actually perform better than the tensor network, and it doesn't, although it gets pretty close, it does really well. And then as we feed it data from the device, we actually see that it gets better and better than the tensor network. This isn't terribly surprising. The prior that we use for the tensor network is a stochastic model. It has limitations. We might get the prior slightly wrong. But this does show that there is a little bit of juice to be had by learning from the device itself and teaching this decoder what kind of noise is actually happening. And one kind of thing I want to mention about this that I think is really cool is that with the tensor network, if I recall correctly, the distance 5 code was performed better than the average of the distance 3 codes, but with this machine learning decoder, the distance 5 code actually performed better than all of the individual distance 3 codes. So it was really making kind of the distance 5 code better than the sum of its parts, which is, I think, pretty cool. And I want to emphasize there's actually been a couple of papers on machine learning decoding recently that I think are pretty interesting. Okay, the last thing I want to mention is that Craig actually did an amazing job of taking the data from the experiment, curating it, and putting it online, sort of the master of open source. And so there's this link down on the bottom right where you can take all the data that we had from this experiment, look at it, do what you want with it, see if it matches what you'd expect for your models, see if how your decoder does on it. And we've already seen a few papers and other groups looking at this data, and this is super exciting. Like, we love this, and hopefully as we continue to do more error correction experiments in the future, we will be able to publish more and more data that'll be useful for the QC community at large. Okay, so that was kind of the success story. That was saying, all right, well, we were able to push this device to its limit, and we saw the distance 5 code performing better than the distance 3 code. Now let me tell you about, I told you a little bit about some of the things we worry about. The low T1s are definitely a concern. Here are some other things that are scary that we need to address. So the first thing when we were running this experiment was we had this beautiful distance 5 chip that we had calibrated up. We had run the repetition code in 2021, and so we said, hey, let's run the repetition code on this experiment, see what happens. So if I recall correctly, I think it was one of my colleagues, Andreas, who started this, and to embellish a little bit, he was running this repetition code and seeing these numbers come in and saying, oh, well, this is great. We're already down to 10 to the minus 3. Awesome, we're already into the regime that we were in when we were running this experiment 2 years ago. Okay, this is looking a little weird. It's bending slightly. That's not good. What's this? Oh, that sucks. And so Andreas came to the QEC team and was like, hey guys, I'm not an error correction expert, but is this supposed to happen? And we all looked at him and we were like, yeah, this is okay. Of course, it was not okay. This is a serious concern. As we get to the bottom here, we are seeing some error floor. And so we looked at the data to see, what was causing this essentially, this thing that's preventing us from going to even lower logical error rates. We definitely don't want to hit an error floor. And when we bin the data by time, what we saw is that at some point during the experiment, there was some some event, which we think is a high energy event, that caused all of caused all the repetition codes to kind of jump up in error rate. This is super bad. We do not want this to happen. Now, we think that this is kind of the main culprit because when we remove this section of data, which corresponds to about 0.15% of the total amount of data that we took, we do indeed see that the error rate continues to slope downwards exactly like we'd want, all the way down to 10 to the minus 7. And by the way, getting down to 10 to the minus 7, I know it's the repetition code, but I think that is really cool. So what do we think is causing this really? So there's this really, really awesome GIF that I like to show whenever I give this talk, and I want to give credit to Matt McEwen, who made this, where we can run an experiment, which is essentially you prepare the one state, you hang out for a microsecond, and then you measure it, hopefully in the one state. And if you do this very, very quickly over the entire chip, you can get some figure, like you see on the right-hand side here, where it lights up when you get errors in this experiment, when you see the 0 state. And so there's this moment around 0 milliseconds on this curve where you see not just that it lights up, but it lights up in a particular place on the top left part of the chip. So there is some spatial resolution here. And what we think that is some high energy event hitting the chip and basically causing the T1 times of our qubits to tank. Moreover, if you look at this sort of the number of errors that we're seeing, it declines over tens of milliseconds. That's actually quite a long time for us. So you get this enormous correlated error in space that also has quite a large extent in time. This is the type of thing that we do not want to see for error correction. We don't like this. It would be really hard to fix this using error correction. However, we're very buoyed by the fact that there have been a ton of works recently looking at how this can be fixed at the hardware level. And so I think at this point, we're fairly confident that we have a handle on, or that we've seen all these basically awesome proposals for fixing this problem at the physical level instead of at, for example, the error correction level. That's really good, because this would be a really big problem. The second issue that kind of comes up and is just par for the course for transmon qubits, which are these slightly nonlinear oscillators, is leakage. Leakage happens all the time in our system. Everything that we do can kind of cause leakage. So in particular, here's like kind of a nice experiment that we run where we inject leakage into a data qubit and a surface code. And then we run many cycles of surface codes, and after each cycle, we do one of these measurements to see how that leakage is spreading or how it's, hopefully going away. And what we see is that we run one of these cycles, the leakage doesn't just stay put, causing errors around it, which it will do anyway, but it also kind of moves around the device and hurts other qubits. So there's this kind of not ballistic, but the spread of leakage in the device. Now, it's not too hard to see why this is happening, right? When we do our 2-qubit gate, we're setting our 2-0 state on resonance with our 1-1 state, but in turn, we're also creating higher resonances between higher energy states. And this means that these resonances can swap leakage. A leakage event can cause another leakage. And so this is something that we absolutely need to fix if we want to run error correction for very many cycles. So the first tool in our toolbox to deal with this is something that we call multi-level reset. It's actually the one component I didn't tell you about in the beginning of the talk. When you're resetting a qubit, it doesn't come for free that you can reset the 2-state or the 3-state. It's not just all the photons leave the qubit. You have to design that. And so the way that we do reset in this experiment is we have our qubit above our resonator in frequency. We sweep it below the resonator and kind of donating photons to the resonator as we move by adiabatically. And then we wait for that resonator to have all its photons deplete, and then we bring the qubit back up to its idle frequency. And this allows us to not only reset the 1-state well, but also the 2-state and the 3-state, maybe the 4-state, we don't know as well because it's hard to kind of tell. But this is something that is extremely helpful in removing leakage from the system. So when we integrate this with the experiment, what do we see? Well, first of all, leakage is highly suppressed, relatively speaking. The measure qubits don't have a lot of leakage left on them because they're constantly being reset. But still, the leakage that was present in that initial data qubit is persevering, so that's one issue. And then we can see that due to some probably bad configuration of frequencies, it is still finding its way to this top right data qubit. So there is still kind of some hopping, even though we're resetting the measure qubit every round. Now, it would be great if we could just reset the data qubit, but we know that we can't do that directly. There are, of course, proposals for swapping measure qubits and data qubits to be able to reset all the qubits frequently. But one thing that we think is kind of nice and pretty easy to implement and requires less overhead is something that we call data qubit leakage removal. So we already have a 2-qubit gate that pairs a leaked state, but it transits through a leaked state to our computational states. And so what we can do is we can basically use that interaction to suck photons or like leakage photons out of the data qubit. So in particular, instead of doing a CZ gate, we can do a half of a CZ gate. So if you have some leaked data qubit, after you reset the measure qubit, with high probability, it'll be in the 0 state. You run this leakage I-swap gate, and it will take that leaked photon and kind of take one photon out, deposit it in the measure qubit, and convert it to a Pauli error in the data qubit. You can then run a fast reset gate if you want, or you can just deal with a measurement error. But you can run a fast reset gate to try to get rid of that extra photon that the measure qubit has picked up. And indeed, when we do this, what we see is that the leakage is actually highly suppressed in the system. So not only does leakage not spread, but that initial leakage that we injected into the data qubit quickly diminishes. And that's really great. And so by the end of the experiment, we're seeing kind of this steady state leakage population around at least somewhere around 10 to the minus 3, or 10 to the minus 3 or below, and that is exactly where we want to be for error correction to be working as we'd like. That's kind of an acceptable level of leakage in our system. Now, of course, this isn't the whole story. There are other worst leakage events. Things can be induced by measurement, for example. Photons in the resonator can induce really bad leakage in the data qubits. You actually saw that a little bit in that leakage slicing plot with the measure qubit. But we think that we are developing really good tools in our toolbox for kind of handling leakage as much as we need to get error correction to work, I think. A little biased. So anyway, to conclude with what I was talking about, what have we shown? We've shown a surface code where the distance 5 code performs slightly better than the distance 3 code in terms of logical error per syndrome extraction cycle. Realistically, a 5% gain is not going to get you to 10 to the minus 12. In fact, even if we achieve the absolute best performance we could on this device and hit a lambda of, say, 2, if you calculate the overhead from that lambda using the surface code, it's going to be extremely expensive. And so we can't just be at threshold or below threshold. And in this particular experiment, we argue in the paper we're not quite below threshold, but we're close. But you need to be well below it. And so we think that we need to improve our device by a factor of at least 3, and 10 would be nice, in order to get these like scaling factors where you actually are implementing really low logical error rates to implement really long fault-tolerant algorithms with surface codes whose footprints aren't crazy large. Now, there are some challenging error sources we have in our device that we've talked about a little bit, like leakage and cosmic rays. But I think we're actually feeling pretty good about all of the sort of ideas that are coming from our group and in the community for handling these things, and so we don't think these are going to be showstoppers. However, as we saw in the repetition code from 2021, it is super important that we test these things at lower logical error rates and at larger sizes to identify where, if there is some sort of physical barrier to us going below some error rate, if there is some sort of engineering barrier. I think using repetition codes is a great test for that, kind of like a canary in a coal mine. You get to the bottom, this like bottom error rate, or these really low logical error rates, and you see what's going wrong. And that's exactly what we intend to do, build larger and better devices. And so I want to end by just saying that I work, again, with an amazing team of people, and even more importantly, an amazing team of pets. And thank you very much.
We'll start with Ben.
Hi, Michael. I got a lot of questions. Some are really sophisticated, but I want to. It's early in the morning. I asked.
Wow, I hate that. Continue.
No. It's gonna be real dumb. So, in terms of cosmic rays, what would it really take to block cosmic rays? You know, the dumb way, with a big wall of something thick, you know, lead, water with boron in it, or whatever that just goes around the
That's
device.
a great question. The answer is a miracle. It would be really, really hard. I mean, people have done experiments where they've gone under mountains and done a ton of lead shielding, and you still see these high energy events happening. So it's really not a good strategy, I would say. Or not, you never say never, but it would be really hard. Yeah.
So we have time for one more question. I'll give it to neutral atoms.
That seems directed.
Thank you for the really nice talk. So, okay, yeah, in a similar spirit. So I guess you mentioned at the end about how useful this repetition code experiment was. You also showed this really nice data about, you know, monitoring leakage. I guess, what have you guys, out of all of these different characterization experiments, what do you think in kind of, you know, doing everything that you needed to do to get to this stage, what was kind of the most important one and kind of seeing what all the challenges are, or kind of the most important few and seeing what the challenges are and kind of allowing you to push your system?
Yeah, so you're saying like developing all these experiments to sort of identify these like bad air sources and
Yeah, exactly, things like that.
Yeah, unfortunately, I'm not going to be able to say like, oh, it was the leakage slicing or something. I would say that this is a little bit of a cop-out, but I would say that really there's no substitute for running the whole experiment and looking at the top line number. We certainly knew about cosmic rays before we were doing the repetition code. So there are other experiments where we were seeing that. But I would, you know, at the same time, I would say we're frequently developing protocols that are aimed at identifying bad error sources that we think about. So like another thing that we worry about frequently is like measurement-induced state transition. That's really bad leakage, where the photons in your resonator basically, they cause your data qubit to leak to infinity, well, to 6 or so, something really, really bad. And so finding ways of characterizing how much that happens would also be very important. But to answer your question, I think there's no substitute for running the whole experiment. Yeah.
Thank you.
So with that, I, like Earl, like to be on time, so thank Mike again.